Okay, hello everyone. In this video, we are going to work through calculating delta S of the system, so quantifying it. In the previous video, we really talked qualitatively on whether we would predict this to increase or decrease. But this video, we're going to apply the formula that we talked about in part 3 video to be able to actually numerically determine the sign of delta S of a reaction. And so in this example, it asks us to calculate delta S for the reaction for the balanced chemical reaction that is ammonia plus oxygen forming nitrous oxide plus water. And it gives us a subset of the data that comes from the table in Appendix II in your textbook. And so we know from video number 3 that delta S of the reaction is going to be equal to the sum of the moles times the S of the products minus the sum of the moles times the entropy of the reactants. Okay, so to do this, what we're going to have is that delta S of the reaction is going to be equal to, I'm going to start with the products. So I have 4 moles of nitrous oxide times the 210.8 joules per mole times Kelvin plus 6 moles of water times the 188.8 joules per mole times Kelvin minus the same thing for the reactants. So for the reactants, I have 4 moles of NH3, and NH3's S value is 192.8 joules per mole Kelvin plus 5 moles of O2 times our 205.2 joules per mole times Kelvin. And so if I do this math, I get that delta S of the reaction is 1976 joules per Kelvin minus 1797.2 joules per Kelvin, which gives me that delta S of the reaction is equal to 178.8 joules per Kelvin. Okay, so I hope this gave you one example of how to find delta S of the reaction. And in the next video, we're going to continue working with this concept of spontaneity, and we are going to begin to introduce we're going to talk about the differences between the entropy of the system, the surroundings, and the universe, and really talking about predicting spontaneity based upon entropy. And so kind of putting all of these ideas together in a numerical way.